Okay, so if we're talking about multiple variables, people think graph first. And don't ever think about a graph if it's bigger than 3 dimensions. Variables are whatever you're using for input. So you have a company, you make 10 different products. It's an 11-dimensional problem because you have 10 independent variables and then 1 dependent variable, whether it's cost or profit or revenue. The number of variables is the dimension you're dealing with. And that sounds scary. No, it's only scary if you're trying to draw a representation of it. You don't need to draw a picture in order to do. Those of you who have had Calc 3, you worked with multiple dimensions all the time. You didn't have to draw a picture every time, but when you could draw a picture, you did. So last day we did a problem, 2 independent variables. It was really easy to understand. But in reality, let's suppose I make more than 2 things, and let's say I have a lot of constraints. Because maybe it's labor as a constraint, how much time, machine time because I have to do things there, certainly money that I have to spend, time that I have to do the project. There's several different possible independent variables, and all of them would be inequalities because you don't necessarily have to use up all of your resources. Okay? But what we saw is you can't exceed your resources. Okay, that makes some sense. So let's take a problem. And we're going to do this from beginning to end so we can see how effective the simplex method is. All right. I'm just grabbing one from the book. There doesn't have to be a specific application. Oops, hold on a second. Use the problem. Make sure I have the right. Oh, here we go. Sorry. I have the right one there. So we want to. They have 3 and 4 variable problems I just wanted to do. There it is. I want to grab all these pens and you got the one with no juices. All right, I want to maximize write down, make sure I don't lose it here. I'm losing my place on here. Okay, I want to maximize P equals 2x1 plus x2 plus 3x3. And it's common to use x1, x2, x3 because I might have 4 variables, 5 variables, and so on. Okay, subject to the following constraints. x1 plus x2 plus x3 is less than or equal to 59. 2x1 plus 3x3 is less than or equal to 75. x2 plus 6x3 is less than or equal to 54. Now I'll just be lazy. x1, x2, x3, non-negative. Now, I could construct a 3-dimensional situation where I can get a holographic machine and have a bunch of planes, and you could see this would probably enclose some polyhedron, okay? And it would be really scary and nasty to try to work your way around that one and try to figure out the points of intersection. But technically, you could do that. It would be difficult. Because what would you do if there was a 4th variable or a 5th variable? So what we do now is we create a system of equations. This last part here is not trivial. If any of these were allowed to be negative, that makes the problem a lot more difficult. Okay, so we usually are sticking with something like this because the idea these are probably resources. So having a negative resource doesn't really make sense. So we start with, take the first inequality and we're going to add a slack variable. Pull it S1 and now that gives us an equation. Do the same thing for the second one. S2 and that gives us an equation. The third one. An equation, and then what I do is I rewrite this by throwing everything on the other side, so negative 2x1, negative x2, negative 3x3 plus p equals 0. And right now, before I start the problem, x1, x2, and x3 are all 0. Right? I haven't done anything, they're all 0 right now, which means the profit would be 0. And that is a viable solution. It doesn't violate any rules, but it's certainly not the best solution. Okay? So now I make my matrix. So 1, 1, 1, 1, 0, 0, 59. Hope I can fit all this on here easily. Then 2, 0, 1, 3, oops, 2, 0, sorry, 3, 0, 1, 0, 75. Then the next one would be 0, 1, 6, 0, 0, 1, 54. And then the last row, -2, -1, -3, and then all zeros. So the way this is read, and that's the column for x1, x2, x3, s1, s2, s3, and then the constants on the right. I am done when the bottom row is no longer any negative, has no negative values. Okay, so if you remember last day.
Excuse me? So you don't include P in the matrix? For the last equation on the bottom?
No.
Okay.
Yeah, that was most of last day's lecture. We already did this. This is just another problem from last day. If you have, by the way, if you haven't done so, do go online. How many have actually looked at the problems in section 9.3? Anybody? Really long. It took many pages to do one problem because the author kind of over-explains the arithmetic unnecessarily, but just wanted to make sure you got it right. It's not really necessary to go to that level of detail explaining. Which column is my pivot coming from?
3.
Why?
It's the largest negative number.
Good. So let's start there. I'm a big fan of doing things like this. Now, I have 3. I'm not looking at this one. I'm looking at these 3 rows. I have 3 ratios: 59 over 1, 75 over 3, 54 over 6. What am I looking for? The smallest positive ratio, because I could have negative numbers in here. In most of the examples, the author actually mixes positives and negatives all throughout the problems. I used all positives. It makes it a little easier to follow. But it's the smallest positive ratio. So of those, which is the smallest positive ratio? 54 over 6. So there's my pivot. Okay? It's an algorithm. There are no choices. Now, there's a what if that people always ask. What if I had 2 different places where I got the same ratio? Which one should I choose? The answer is yes. It doesn't matter. You're still going to get to the same place. Remember how we went around the shape last day? We kind of worked our way around the shape. So if you had choice, let's say I started here and the answer was over here. If I make one choice, it'll take me this way. If I did the other choice, it would take me this way, but I will still get to the same final result. It would just be a different path. I tend to avoid that problem as an example because I think it only confuses. You don't want choices, you just want it to be automatic. But it is possible that you could have the same number show up. The final answer will still be correct and you're still going to get it, but you might get it through an alternate route. So that's my pivot. So my first step is to make that a 1. So 1, 1, 1, 1, 0, 0. I'm going to write a little bit tighter now. 2, 0, 3, 0, 1, 0, 75. And then 0, 1, 6, 1, 0, 0, 1, 6, 9. -2, -1, -3, 0, 0, 0, 0. Okay? I'll keep that one circled so I remember which one's my pivot, because I have another place where there's a 1. I don't want to confuse the two. So I'm going to make this a unit column. A unit column literally looks like a unit vector, right? 1 and all zeros. So we'll do negative row 3 plus row 1. We'll do negative 3 row 3s plus row 2. We'll do positive 3 row 3s plus row 3. All right, plus row 1. So 0, 1, 6, 1, 0, 0, 1, 6, 9. All right, so we're going to do the negative. I'll have 1. I'll have 5, 6. I'll have 0. I'll have 1. I'll have 0. I'll have negative 1/6, and I'll have 50. Next row, negative 3 of these. So I have 2, negative 3 of these. I'm going to write it as negative 3/6. Just makes it easier to keep track, but certainly negative 1/2 is correct. Negative 3 of these. And then here will be a 1. Sorry, negative 3 of 0, 0. Here we go. 1, and you know, I'll put negative a half, I would think. And then negative a half. And then negative 3 of these, that'd be negative 27 plus 75 would be 48. Going the other way, I'm gonna have negative 2. 3 of these plus negative 1 would be negative 1/2. And then 3 of these would be 0, 0, 0, 1/2, 27. Okay, I'm not finished, but if I stopped here, I have a viable solution. Okay, how would I read my solution if I stopped here? X1 would be,
0,
X2 would be,
0,
X3 would be
9.
9. Huh. X1 is 0, X2 is 0, X3 is 9. So certainly I didn't use all of this one. I didn't use up all of this one, but I did use up all of this one. And if X3 was 9, my profit would be what?
27.
27. I would have unused S1 and S2. In fact, S1 would be 50. That's how much I didn't use up. 9. Well, I should go here. And that would be 50. What would S2 be? 48. 0, 3 times 9 plus 48. See, it would still work. Now, is this my best answer? No, because the bottom row still has at least one negative in it. But it is a viable solution. So last day when we did 2 variables, we saw we worked our way around the enclosed polygon. Now you'd be working your way around the enclosed polyhedron if you wanted to think about it that way. So now, what is my new choice? First column or second column? First column. 50 over 1, 48 over 2, 9 over 0. 9 over 0 is not a choice. A lot of people will choose that. That doesn't make any sense. That's undefined. It's got to be the smallest positive ratio. So is it 50 over 1, 48 over 2?
48 over 2.
48 over 2. So that's my new pivot. I only had 2 to choose from. So now I'm going to do 1/2 of row 2. All right, so 1, 5, 6, 0, 1, 0, negative 1/6, 50. 1, negative 1/4, 0, 0, 0, 0, 1/2, negative 1/4, 24. So help me out, I don't want to make any mistakes here. I think that's okay. And then 0, 1/6, 1, 0, 0, 1/6, 9, negative 2, negative 1/2, 0, 0, 0, 1/2, 27. Okay? Well, I don't have to do anything in row 3, then a little less work. So negative row 2 plus row 1. I'm going to do 2 row 2s plus row 4. All right, so the negative in that way. So now be a little careful. So I have positive 1/4 plus 5/6. What does that give me? Positive 1/4 plus 5/6. So 3/12 plus 10/12. So 13/12. All right? And then 0, 1. The negative of this, so that'd be negative 1/2. The negative of this, so positive 1/4 minus a 6th, that'd be a 12th. Negative 24 plus 50, that'd be 26. 0, 1/6, 1, 0, 0, 1/6, 9. Okay? 2 of these plus this, that's 0. 2 of these, that'd be negative 1/2 plus that'd be negative 1. 0, 0, 1. 2 of these pluses, that'd be 0. two of these, that'd be 48 plus 27, that's 75. Okay? I finished round 2. Is there a viable solution here? Yeah, let's read. Again, I don't need you to do this when you're actually doing the problems. I'm demonstrating this, that at every round we always get something that didn't contradict, that actually works but isn't necessarily the best answer. Okay. So what does this read now? What does this say? How do I read the first?
X1 is 24.
X1 is 24, X2 is
0.
0, and X3 is
No.
9. So let's go over here. You said 24, 0, 9. I'm going to write it down this time. All right, so if X1 is 24 and X3 is 9, that's 33. Oops, sorry, 33. Boy, that's a lot of unused, isn't it? S1 is 26, isn't it? Does that work? 24 plus 0 plus 9, there was 26 unused. That's what that said. Next row. 2 times 24 is 48, plus 3 times 9 is 27, that's 75. So I used up all of this one. S2 is not a unit column, so it would be 0. That's perfect. And then finally, 0, 6 times 9, that's 54. There's no S3. And again, notice that's not a unit column, so S3 would have been 0. So that is absolutely matches what that says, plus going to here now. I'm sorry, going to here. 2 times 24 plus 0 plus 3 times 9, that's 75. That's what that says. We wanted to maximize the profit. We're not done. After round 1, we got a profit of 27. After round 2, we got a profit of 75. Do you think the final answer is going to be 75? It's probably going to be up or down. Probably up because we're not done, so there must be a better answer. Well, don't really have a choice. Got to choose that one. 26 over 12/13. That's 24. 24 over negative a fourth, not an option. 9 over 1/6 is 54. So that makes it pretty simple. Okay, that's there. Now, I want you to know something. My first pivot was in the third column. My second pivot was in the first column, and my third pivot's in the second column. That's good. If I got a pivot in the same column, something probably went wrong. Because if I repeat a column, then I'm going to undo all of the work that the previous pivot had done, making that a unit column. Does that make sense? It's like, oh yeah, that would probably not be a good thing. So we're going to go 12/13 row 1. And this should be the last round. Hopefully I can fit all this up here. All right, so 0, 1, 0, 12/13, negative 6/13, 1/13, 24. And then 1, negative a fourth, 0, 0, 1/4, or excuse me, 1/2, negative a fourth. Again, get out your calculators because we're going to need them. 0, 1/6, 1, 0, 0, 1/6, 9, 0, negative 1, 0, 0, 1, 0, 75. Okay? So I want 1/4 row 1 plus row 2. I want negative a sixth row 1 plus row 3. And I want just simply row 1 plus row 4. And if all goes well, this should be my last step. All righty. So 1/4, so that's a 1 and a 0, 0, 3/13. 1/4 of negative 6/13 plus a half. Use your calculator. Specifically, use the fraction key on your calculator. I'm having you do these so you get used to doing these. Make a number? You all have calculators in front of us and no one knows how to use them for fractions?
5/13.
Close.
Yeah, I got 5/13.
Good. How do I know that's a good answer, by the way? There's something you probably noticed about now. You see the same denominators throughout a column typically. And hopefully you caught that. Oh yeah, that seems to be a common theme. Not for the row as much as for the column. Okay? 1/4 of this plus this. Good, -3/13. And 1/4 of this plus this would be 30. Okay? Now, the numbers in here are less critical. In other words, I could make a mistake. I really wish you wouldn't do that. You do realize it's not legal for you to take a picture without my permission, especially if I'm in the picture. But sit up here.
I think it's the anchor.
Yeah, but you can't take a picture in my classroom of me without my permission. That's a violation of all sorts of things going on. You know, I'm very uncomfortable when I see people taking a picture and I'm in the picture and I didn't give you permission. But that's not cool. I'm recording the lecture, by the way. You really don't need to take pictures. And I've been in every single picture, which really creeps me out. Just so you know, it is illegal and it creeps me out. So please don't do that. Take a picture of the board when nobody's standing there. Not when I'm in every picture. Oh, I just sit there. There's a great seat right there. Yeah, Ellen.
I don't know if I'm the only one, but it's difficult for me to see.
It's small. That's why I'm saying them out loud as we go. Yeah.
The red or the orange ink. I don't know
Oh.
what it is. I just can't see it.
Okay. I'll say what they are. Can you see them on the videos?
If I zoom in.
No. I mean, does it show up on the video for you?
Yes.
Okay. So the next row, we're going to go -1/6. So the first few are kind of easy. So -1/6 is going to be -2/13. -1/6, that'll be +1/13 plus that, so it'll be 14/13. Oops, I'm on the wrong row, sorry. Sorry about that. I'm on this row. So -1/6 of this would be 1/13. -1/6 of this plus this would be -1/6 of 1/13 plus 1/6. (2/13) good. And then -1/6 of these, that'd be -4 plus 9 would be 5. Now the bottom row, this should be the easy one. 0, 0, 0, 12/13. -6/13 plus 1, 7/13. 1/13 plus 0, 24 plus 75. Are we done? Yeah. Are we done? How do you know?
No negatives.
No negatives on the bottom row. Negatives within is okay. No negatives on the bottom row, I'm now done. And in this case, I have 3 unit columns. That's a bonus. I want to point out, you do not have to have unit columns for each variable. That's not an automatic thing. Okay? We do in this case. So how do I read this? I'm going to move this way so I can see. How do I read? Well, first of all, let's write it as an ordered triple in this case because we don't really give it any context yet. So what would the answer be in this case?
30, 24, 5,
And the profit would be,
99.
did we use up all of our resources? Whatever those inequalities were representing. One might be time, one might be money, one might be equipment, whatever. Did we use up all of our resources? S1, S2, S3 would all be 0, wouldn't they? So in this case, we did. That's actually unusual. It just worked out nicely in this case. That's not an automatic thing. And in this case, none of my variables were 0. So let's go back and make sure that they actually work. Okay? So in the first one, 30, 24, and 5 do add up to 59. 2 times 30, 3 times, sorry, what was it? Oh, I'm sorry, 2 times 30, 3 times 5 adds up to 75. That's a good thing. And the last one, 24 plus 6 times 5 does that up to 54. So all of them were completely exhausted, and now when I go back to here, 2 times 30 plus 24 plus 3 times 5 does add up to 99. Now, could we have found this solution algebraically some other way? Actually, we couldn't have. There's no way we could have solved the simultaneous system of inequalities with 3 variables. There is no other mathematical procedure. Is it long, slow, and tedious? Yeah. Now, I've got a 10 variable problem, let's say. I have something really big. How many here have just basic programming skills? You can write a do loop, you can write a if then, you can write some basic, simple stuff. I give you a system of inequalities. Can you write these equations? Yeah, it's pretty trivial. Could you then program the computer to do this problem for you, but not using regular matrix algebra, by choosing the right column and then choosing the right pivot by doing if then else kind of stuff? Could you write a program? I'm not asking you to write a program. Could you, with your basic programming skills, write a program that would execute this? Actually, I think you could. And I think if you were actually in a programming class where you were actually sharp and up to date on your skills, you probably wouldn't find it that challenging. So if this were a 10 variable problem, do you want to do this by hand? Oh, heck no. Oh, my goodness. Right? It's too tedious, the fractions and all that. But once you understand the process, could you write an algorithm? That's all you're doing with the programs. You're writing an algorithm to do this. That wouldn't be that complicated, would it? And then you could now solve this multivariable problem. Is that a good skill to have? It's actually a huge skill to have. Yeah, linear programming is a huge skill because in real life, things do work this way. Large systems of linear inequalities would be a nightmare to solve by hand, but once we understand the algebra involved, yes, you could use technology to do this because there aren't an infinite number of solutions. There's only one. Now, what you're going to find happen often, a problem like this, maybe I have more than 3 variables. And so maybe each variable represents, these aren't points in space. X1 represented maybe, how much of this particular crop I want to produce. X2 was this particular crop, and so on. Or maybe we're a car manufacturer. X1 was a particular automobile make. X2 was a different one, and so on. So my answer doesn't necessarily have to look like this. I could just say X1 equals X2 equals. No problem, because this isn't a point in space necessarily. They represented something. You could work through a problem and find out you have a variable that's 0. Now that's an interesting problem because this is a very, very real life problem. It happens often. You did the entire problem from beginning to end and you came up with a variable of 0. What would that mean?
It's not profitable to use one of your resources?
Not the resources. It's not profitable to produce that thing.
Oh.
But if these were cars, that means I stopped making that model of car. Have you ever had something you purchased semi-regularly and it disappeared from the shelves? Has anybody ever had that happen? Oh yes, I still remember with great despair. O'Grady's au gratins. They were a potato chip. Arguably the greatest human invention other than maybe the dishwasher, because I really hate washing dishes. They were a thick cut chip with this layer of cheese. It was probably all artificial and bad for you, but this layer of cheese flavor, it was heavenly. And me and my roommate, we lived in PB by the beach, and there was I think it was a 7-Eleven or something, and we would buy them out every week, and that we would just, they were the greatest things ever. And then one day, now I don't remember which company produced them, to be honest. One of the potato chip companies. One day we go in there, they don't have them. And I asked, where are they? Because we stopped getting them. I think they've stopped making them. This was really a long time ago, so I wrote a letter So why didn't you email? We were 10 years away from email existing yet. I wrote a letter to the company and I said, why? And they said they deemed it was no longer profitable for them to produce that product. I figured it out. Me and my roommate were basically keeping them in business because I think we may have been the only ones buying that product, but I remember how sad I was for a very long time, and no one's ever filled that void. But this happens all the time in real life. A company will make a whole bunch of stuff, and then they realize it is profitable for us to no longer make this thing. We will make more money by not making that thing, by putting our resources and spreading them out. This does happen in real life, and this happens quite often. That's why anything would be discontinued, because the company deems it's more profitable not to make that thing anymore. And that's kind of a bummer if that's something you bought, but if you think about it logically, you'd say, yeah, if the bottom line was to maximize this value, and it's what combination of X1, X2, X3 gets me there, one of those might be a 0. And there's nothing wrong with that. That's just the way it is in reality. So it's an interesting problem, and that's how you would make that conclusion, because you calculated 0 and said, oh, I guess it's better not to have that thing. Okay, now we're going to move on in a moment. Any question on this?
Yes. How come, I know that you said that this is the case, but why is it that if you have multiple lines in a column that you can just say that that's 0?
I'm sorry. Okay. The answer can only come from a unit column. A unit column, so this is the X1 column, so X1 is 30 because it's a unit column. But let's go to here. This was not a unit column yet, so the value of the variable right now is 0. Only, the answer can only come from, that's the whole point of the simplex method. The answer can only come from a unit column. So my slack variables ended up, none of them were unit columns, which means all my slack variables were going to be 0 at the end of the problem. And the translation is all my resources got used as a result. And then we can see when we were checking that all those numbers actually do work. But that's part of the whole simplex method. What makes it work is that you read your answer from unit columns. Yes, along the way you have icky fractions. But like I said, if you're using a computer to help you do this, are you really working with icky fractions? No, you're letting something else do it. You know, you're not really worried about that. Yeah.
Could you explain how you can tell just by looking at the matrix there won't be any leftover?
Well, because this was the column for S1, S2, S3, and none of them are unit columns. Remember earlier when I said at this, at this point we have a viable solution because we just finished about a unit column. Let's go back one notch. Right now, I have something that would work. X1 is 24, X3 is 9, but X2 is 0 because it's not a unit column. Now go over to the slack variables. S1 is a unit column, so S1 is 26, but S2 and S3 would be 0 because they're not unit columns. Then when we went over and checked it, we saw all those numbers worked. So when I say a viable solution, it's something that actually would satisfy all those. But our goal was to maximize P, not just get an answer. So last day when we looked at the enclosed polygon, we know that every vertex of the polygon was a viable solution. Every one of those could work. And so when we did it last day algebraically, we had a 2-variable problem. And so we said, let's take each of those ordered pairs, stick it into there, and whichever gives us the biggest answer wins. But remember, if I change the coefficients, if I change the coefficients on these, are we going to get the same final answer? No, we'll be at a different place. See, these guys here do not affect the enclosed polyhedron. That's only affected by these guys. Oh, so if I had multiple points on this, if it helps you think of it as a cube, an enclosed polyhedron, every one of the vertices is a possible answer. And if I went through every vertex on that thing and plugged them into here, whichever gave me the biggest number wins. But you realize how difficult it would be finding all the vertices, first of all? Because you're in 3D. We have more variables, that becomes overwhelming, that kind of task.
So if you're maximizing, could one of the ones where one of the x variables is in the unit column, could one of those be the maximum rather than at the end we have the 90?
Could I have been done sooner if this, let's say that was positive 1. Is that what you're asking? Let's say this was positive 1, then we would have been done here. and that would have been our answer. We would have had an x1 and an x3 of values, and an x2 would have been 0 if that was positive, because we'd be done. There's nothing left to do. And another way of thinking about it is, I'm trying to make something a unit column, but if this was a positive number, there's nothing to get rid of. I'm only getting rid of the negatives on the bottom row. I'm not getting rid of positive numbers. Now, what if? What if along the way of getting rid of these negatives, I produce negatives somewhere else? Well, then I just keep going. I have to have all the negatives gone. But what you're going to find is, we started with all positives. I did that on purpose. I chose a more representative example where all of my resources were positive coefficients as opposed to some negatives. If any of those along the way had had negative values, this is a little bit trickier in some cases, okay? And it also means getting rid of one negative might produce one somewhere else down the road. I'm not done until I get rid of all the negatives. That's the most important part. If I go out of order, if I choose the wrong pivot, I just simply make an error and choose the wrong pivot, I will get a viable solution at the end, but it won't be the right answer. Again, it's like going around that polygon and stopping at the wrong vertex. That's literally what would happen.
Can you do minimization problems as well?
That's kind of what we're doing next. This one's a little bit more challenging. Okay, we're going to do something that's called the dual problem. We're going to look at a minimization problem that cannot be done using a matrix. But we're going to change it into one that can be done, read our solution, and then go from there. So I'm going to start with a simple problem again, like I did last day. A two-variable problem that I can graph and we can see so that we have something to compare our answer to. Okay? I'm going to erase all of this. Now in Calculus 1 and in Calculus 3, we consider the optimization problems the most important applications because maximize, minimize. Usually, in real life, those are the only ones that deal with money. I have the situation I want to maximize or minimize. I got to take derivatives, do all that stuff. But those techniques aren't very effective when all my boundaries are linear because derivatives of linear functions are always 0. I don't have any critical values, right? So this is how I do the linear stuff. The nonlinear stuff I need calculus for. You put the two together, you can pretty much solve any problem that exists because you can also use technology to help you on the bigger problems. So let's consider the following. Okay, I wrote down a simple problem. I want to minimize, let's call it the cost. I'll just make up something simple. Okay. Subject to 3x plus y is greater than or equal to 27. X plus y is greater than or equal to 15. X plus 4y is greater than or equal to 24. X and y are greater than or equal to 0. I now want to minimize. So think of this as now, these are cost things. And I have to now use at least this much stuff. Okay? I may be making something, maybe I'm making a cake, I don't know, but I got to use at least this many ingredients. Okay? I have to use at least this amount of money. I have to use at least this many resources. Before it was at most. Okay? But my inequalities are going the other direction. So I cannot add a slack variable to these, can I? Because that would mean my slack variables would be negatives, and that really wouldn't make any sense if I'm talking resources. But let's do this as a graphing problem. Okay? I'm going to just sort of give you don't worry about the extreme accuracy of my drawing. So that, I have that, I have that. Okay, more or less. Okay, so the first one, I want y is less than or equal to negative 3x plus 27, right? Slope of negative 3. The second one would be y is less than or equal to negative x plus 15, so a slope of negative 1. And then the third one, y is less than or equal to negative 1/4 x plus 6. Did I say that back? Oh, I'm sorry, these are, my bad, sorry, these are all greater than or equals, sorry about that. These are greater than or equals. Now, which side do I shade? We talked about this last time. All you gotta do is pick one point on the oval XY plane, doesn't pass through the lines. I don't know, how about 0, 0? Is 0 plus 0 greater than 27? No, so I should be on the other side of the first line. Is 0 plus 0 greater than 15? No, so I should be on the other side of that line. Is 0 plus 0 greater than 24? No, so what have I got basically? I'm on this side. Does that matter? Yeah, it's open. It goes forever. Is there a maximum value now? Is there a maximum value of C? Or can X and Y literally both approach infinity? They could, except what I was trying to minimize. Oh, in the previous example, we enclosed something and we're thinking our answers were on the outer limits, right? I'm trying to minimize, so what do you think my answer is going to be now? I want to go this way. See, if I go this way, C will grow without bound. So I think I want to go this way. So my answer still should come from the vertices. But what picture do I now have? Here's what I have now. And because I said X and Y had to be greater than or equal to 0, this has to be in the first quadrant. Okay? So, if I set as equations, if I set these two equal to each other, it's pretty easy to solve. I'll just go ahead and tell you what they are. Save some time. So this point would be 6, 9. This point would be 12, 3. Real quick check. 6, 9 equals 27. 6, 9 equals 15. So it's on both lines. Now, 12, 3 equals 15. 12 equals 24. And then the last one here would be, this would be 24, 0. Okay, 24, 0. And the top one, this would be 0, 27. Okay, so I have, in this case, exactly 4 possible answers. All 4 of these could be the answer. If I change this coefficient, let's say I make the x coefficient really, really large, then my answer is probably coming from this direction. If I made the y coefficient really, really large, then the answer is probably coming from this direction. If I make x and y fairly close together, then it's probably coming from one of the middle two. Right? I can play with the coefficients all I want, and that would change the answer. So all we have to do is take each of those points and stick them into the plus. So, and then 24, 0. So 0.27, my cost would be 108. At 6, 9, so it would be 36 plus 36, my cost would be 72. At 12, 3, that would be 72 plus 12, my cost would be 84. And 24, 0 would be 144. So right now, do you agree that when x is 6 and y is 9, I would have the minimum cost? Again, if I change the coefficients, it changes the answer. Great. So what I want to do now is do this problem using the simplex method. But I cannot do this problem using the simplex, so we create what's called a dual problem. And we use the simplex on this. Now, I saw the proof of this in grad school, and I'm still confused by it, but it is very long, gnarly, and abstract, and you're not going to see the proof in a lower division book. It's just how, the execution part.
Is it dual as in like 2, or dual as in like fighting? Like, how do you spell it?
D-U-A-L. It's think of a dual as like alternate.
Yeah.
So we're solving, it's kind of like saying we're solving 2 problems simultaneously. So what we do is, first thing we do is we're going to put all the numbers, it's what's called a tableau. It's basically like a matrix. They call it a tableau. So I'm going to take the numbers, and I'm going to stick them, and here's what I'm going to do. 3, 1, 27, 1, 1, 15, 1, 4, 24, and in the last one, 6, 4, and then I'm going to leave this open, leave it blank. I want to take the transpose of the tableau. The transpose is where the dual problem is going to come from, okay? So I'm going to put a little T on here. So if I put a transpose, what will I get? I get 3, 1, 27. I'll get 1, 1, 15. I'll get 1, 4, 24. And I'll get 6, 4, and then blank spot. Did I write those correctly? Hopefully I did. Okay. I want to, now, I'm going to change something about this problem. Okay, I wrote it with X's and Y's because that was the problem I solved. I'm going to change the way I wrote it because I can't use X and Y. I'm going to now change it to X1 and X2, and I'll show you why in a moment. This is the problem that we did from baby algebra. We did it from beginning to end, we're done. But the new problem will start like this. The new problem will say, minimize, this is the math 254 problem. C equals 6x1 plus 4x2 subject to, and I'm going to write the same problem, but this is the problem we're actually going to see. 3x1 plus x2 is greater than or equal to 27. x1 plus x2 is greater than or equal to 15. x1 plus 4x2 is greater than or equal to 24. x1, x2 are non-negative. The reason we're going to do this is we're going to make a dual problem, but we have to choose different variables. The original problem, we're going to use x1 and x2. What do you think we'll use for the dual problem? Well, y's. Yeah, let's make it easy on ourselves. This is the problem from baby algebra. X and Y made perfect sense because you're in remedial algebra, you're doing two variable problems. But this is not how the problem is going to be done in our class. The problem is actually going to be stated in exactly these terms. This is exactly the same problem, but now the dual problem will be maximize. I now have 3 variables in my new problem. I'm going to have 3 variables. Whoa. So I want to maximize P equals 27y1 plus 15y2 plus 24y3 subject to, do you remember where these came from? I had these inequalities and I wrote them down. Now I'm doing the simplex problem on a different problem. They're now going to be less than or equals. Subject to what? 3y1 plus y2 plus y3 is less than or equal to 6. I'll write it horizontally so I can fit it up here. y1 plus y2 plus 4y3 is less than or equal to 4. And finally, oh, that's it. Just those two. Okay? So here's how it works. In the original problem, I had 2 variables, but 3 constraints. In the dual problem, I have 3 variables and 2 constraints. They flip-flopped. So the answer I get to the dual problem obviously isn't really going to work because I'm going to get a y1, a y2, and a y3. Not exactly. We read our answer a little bit differently in the dual problem, but we attack it the same way as we did before. So when I do this, I now need to create my slack variables. Let me erase this. I don't need this. I'm going to leave that picture up because my final answer I want to be able to go back and justify it versus that one. So I don't need this anymore. So now let's create our system of equations. And there's a lot of setup involved. Our system of equations will now be 3y1 plus y2 plus y3 plus s1 equals 6. y1 plus y2 plus 4y3 plus s2 equals 4. And then the top one, negative 27y1, negative 15y2, negative 24y3 plus p equals 0. The reason we didn't include p as a column is because p is not a variable. P is just the result of adding up the other numbers. Okay, so we mentioned that last day. The columns only refer to the variables or the slack variables, but p is not a variable, it's just the sum of the previous numbers. So our matrix will look like this. 3, 1, 1, 1, 0, 6, 1, 1, 4, 0, 1, 4, negative 27, negative 15, negative 24, 0, 0, 0. This won't take that long. It'll take us a little bit, but it won't take that long. So, where do I choose my pivot from? So I'll go this column, 6 over 3, 4 over 1. 6 over 3. All right, so let's do 1/3, row 1. So I'm going to have 1, 1/3, 1/3, 1/3, 0, 2. 1, 1, 4, 0, 1, 4, negative 27, negative 15, negative 24, 0, 0, 0. All right. Let's do negative row 1 plus row 2. Let's do 27 row 1s plus row 3. So 1, 1/3, 1/3, 1/3, 0, 2. 0, 2/3, 11/3, negative 1/3, 1, 2. Now 27 of these, 0. 1/3 of 27, that's 9. Plus negative 15, that'd be negative 6. 9 plus negative 24 would be negative 15. 27 of these, that'd be 9, 0. 27 of these would be 54. Okay? Now I'm not going to hunt down viable solutions because we're already doing a dual problem. Now, second column or third column? Can't be the first column.
Third.
All right? 2 over 1/3, 2 over 11/3, which is smaller. 2 over 11/3 is smaller. So we'll do 3/11 row 2. So 0, 2/11, 1. 3/11, so it'd be negative 1/11, 3/11, and then 6/11. Yuck. Okay? 0, negative 6, negative 15, 9, 0, 54. Again, our pivot was right here. So we have negative 1/3 row 2 plus row 1. We have 15 row 2 plus row 3. Does that look right so far? I think we did that correctly. All right. So 0, 2/11, 1, negative 1/11, 3/11, 6/11. All right, so negative 1/3, so that's a 1. Negative 1/3 times 2/11 plus 1/3. Negative 1/3 times 2/11 plus 1/3. 3/11. So 3/11. So I have negative 1/3 times 1 plus, oh, that's obvious, there's my 0. Negative 1/3 times negative 11 plus 3. Anybody? You guys have fraction keys in your calculator. Come on. 4/11, okay? Negative a third of that, negative 1/11. Negative a third of that, so negative 2/11 plus 2 would be 20/11. Kind of a yuck. And the other way, 15 of those. So 30/11 plus that would be negative 36/11. 0, 15 of these. So negative 15/11 plus 9, so that'd be 84/11. Yuck. And then what, 15 of these, so 45/11. And finally, that'd be 90/11. What's 90/11 plus 54? That's kind of nasty. What would that be? Very good. All right, we have one more step. One more step.
Shouldn't it be negative 84/11?
I'm sorry, which one?
The third column, fourth, or third row, fourth column.
Oh, negative 6/11 times.
Which one am I'm sorry, which one again?
Third row, fourth column.
No, that should be positive.
Is it negative or positive?
Wait, was
Are you talking about the 84/11s?
Yeah.
Well, I was adding it to 9.
Oh, yeah.
So I was adding to 99/11s.
Never mind. Numbers are huge.
But if there's a mistake, let's I don't want any mistakes because the whole thing will fall apart and we go, what went wrong? I've had that happen. We get to the end going, this ain't working, and someone says, oh yeah, way back there. That stray mark you read as a negative sign. All right, where's our pivot coming from? Okay, 20/11 over 3/11, that's 20/3. 6/11 over 2/11, that's 3. So I think it's this guy. Now, one good thing, our first pivot came from the first column, our second pivot came from the third column, and our last pivot's coming from the second column. That's good that they're all different columns. So 11/2 row 2. Yikes. I didn't say this was going to be short and sweet, but it's going to allow us to solve this problem. Zero, 1, 2/11. I'm sorry, 11, not 2, 11/2. 11/2, so negative a half. 11/2, so 3/2. 11/2, so that'd just be a 3. And 0, negative 36/11. Please have your calculators ready to go. Okay, I think we're there. I think we're ready to finish this off. So negative 3/11 row 2 plus row 1, and 36/11 row 2 plus row 3. All right, I'll do row 2. I got that one down. All right, I need you guys to help me out. All right, so 1, 0. Negative 3/11, so that'd be negative 3. Negative 3/11 times negative a half plus 4/11. Yikes. What goes here? One half. It's kind of nice because it comes out really good. Negative 3/11 times 3/2 plus negative 1/11.
Negative 1/2.
Negative 1/2. It's common, they come out really nice. Negative 9/11 plus 20/11 is 11/11 or 1. Okay? That wasn't too bad. Going the other way, 0, 0, positive 36/11, it's going to be an 18. Positive 36/11 times negative a half plus 84/11, yikes.
6.
Comes out exactly 6.
That's what I got.
Anybody else get that? I like it. 6 is a good answer. Okay? Positive 36/11 times 3/2 plus 45/11. This is why you love your fraction key. Positive 36/11 times 3/2 plus 45/11.
9.
Exactly 9. Well, those are coming out kind of good, aren't they? And finally, positive 36/11 times 3 plus 684/11.
72.
72. Do you see the answer? You do see the answer. Where is it? It's where the slack variables are. Oh, sneaky. Okay. The original problem had 2 variables, 3 constraints. The new problem, the dual problem, we changed it to 3 variables, 2 constraints, which meant 2 slack variables. The 2 slack variables in the dual problem are related to the 2 original variables. Hopefully everybody sees the answer. Right here. This was y1, y2, y3, which don't actually exist. This was S1 and S2, but I'm reading the answer from a different place because this isn't the same problem. This was our alternate universe problem, I like to call it. And the answer is read from where the introductory slack variables. In this dual problem, the number of slack variables matches the number of original variables you have. I had 2 original variables, there were 2 slack variables. And then you notice the 72 shows up exactly where it's supposed to show up. But I'm not reading the answer the way I would have read it before. I'm not reading it from here and here. Does that make sense? I'm reading it from here, here, and here. Now, one could argue this was much easier. Until what?
More than 3 variables.
Until that third variable shows up. Then it's not possible. So this problem here is how you do, as Zachary was saying at the beginning, a minimization problem is done by basically an alternate universe, I like to call it. You're changing everything and making an artificial maximization problem, solving that one, and then reading the answer from a different place. This one's a little more complicated, obviously, but we got the same answer. It's where the answer came from that's different.
So, for more variables, how would you read the answer in the?
Oh, I do, everything's the same, it's just this matrix would be bigger.
And it would still be the bottom line.
It'd still be. So, hypothetically, I've erased everything. Okay, original problem, I have 3 variables. The number of constraints isn't even important. I have 3 variables, I have 4 variables. I have a lot of variables, okay? So this is given. So what I do is I make that tableau, do the transpose of the tableau. Now, right now the number of variables will turn into the number of constraints, and the number of constraints will turn into the new number of variables when I do the switch problem. That's why I purposely made the number of constraints and variables different so you can see that they switched. 2 variables, 3 constraints. The new problem is 3 variables, 2 constraints. But the number of constraints is always equal to the number of slack variables in the simplex method. So therefore, the original number of variables in the new problem will be the number of constraints and therefore the number of slack variables. So let's suppose we 1-up. I give you 3 variables, 4 constraints. Then this matrix has an extra row and it adds an extra column, doesn't it? It's a bigger problem. I do everything exactly the same way. And in that case, I have an extra column that I'd be reading my answer from.
Okay.
Does that make sense?
Yeah.
And I do the work the same way. Yeah, this was horrible numbers along the way. Who figured, the final answer ends up being nice. That's why use the fraction key on your calculator. Just fall in love with it. I mean, my 2 favorite keys on my calculator are the fraction key and the parentheses key. Those are the ones I use the most. They get me out of all sorts of trouble. Okay. Any other questions? Yeah.
At the very beginning of this course, you said fractions are evil and we should avoid them.
avoid introducing them unnecessarily when you're solving a matrix problem. Unfortunately, in this problem, it's sort of the way of the world that every position is going to have a fraction. That's why I want you to use the calculator. Okay, I'm serious about that. Don't use the fraction key on your calculator. Don't try to do it in your head and things like that. Yeah, I've already got all my numbers made.
Would it ever be worth like pulling the fractions out as a coefficient?
No, because it would affect the numbers. It would also affect your last column. And yeah, that's a lot of the answers come from there. Yeah, and by the way, if there were a way to streamline this so that it wasn't so icky, I would show you. There really isn't. So what I do is I just don't ask you huge problems. But understand that what makes this problem harder is not the existence of the fractions. That's not what makes this harder. What makes this harder? That you had to take a fractional multiple of one fraction and then add it to another fraction with a different denominator. That's what makes this icky. That's why you use your fraction key. If you use your fraction key, you're getting the fractions back in 2 seconds. You're not laboring. That's the key. If you're doing just a regular matrix problem and you're doing row operations, I say avoid introducing fractions unnecessarily because you're going to have a fraction in every step. But if that doesn't bother you, when you're finding the inverse of a 3 by 3, are you going to have fractions all over the place at some point? Almost all the time. But you can avoid it as long as possible, but you can't avoid an answer of fractions. If the answer is fractions, you can't do anything about that. But you can just delay. In this one, you really can't because you have to make unit columns, and in the process of making unit columns, you have to multiply by fractions at some point. Again, it's probably the ickiest arithmetic, but it is really cool stuff, though. Okay, so this is the simplex method. This is the dual problem using the simplex method. Now, on your quiz related to this, I've asked you this problem, but I made it only 2 variables. So I made this problem really small, so you don't get blown away by all the algebra. I want to see correct setup and all that. In the original problem, and I gave you an application problem. I took one out of the textbook. I don't know if let me see if I say it correctly. And by the way, in the book, what we did to start was 9.3. This is from 9.4. Okay, it's the dual problem. The question was something like this. You're constructing, an energy drink. And the energy drink must have at least a certain amount of carbohydrates and at least a certain amount of protein to make this work. Okay? So the question is, how much of each should you do to minimize the cost if each of these things have different costs? So in other words, it's a real-life practical problem. It's not a complicated problem. And it could easily be done using this, but you're going to do it using this because, again, I could have given you a third. But I'm making it only a 2-variable problem just so it's not overwhelming and treacherous and all that kind of stuff. Okay? The simplex method, one of the coolest parts about this, though, is how much linear algebra do you need to know to do this? You just need to know how to do row operations. And that's almost day 1 linear algebra. I mean, are we multiplying matrices? No. Are we finding other things? No, we're literally just doing row operations from a different point of view, but that's all we're doing. And this is considered a ridiculously high-level problem. Now, I'll tell you a funny story. Back in the day, I used to teach programming here. I'm not a computer programmer, but I taught the programming because the programming is a math class. We used to do Turbo Pascal back in the 90s, which is a really cool language. You could literally write algorithms to make the computer a calculator. It's better for calculations than most other programs. And so I would teach people how to find the inverse of a matrix or to do the regression, by writing the proper things. And to be in the class, it had a really low math requirement, like remedial algebra was the math requirement, but I would also get linear algebra folks in there. So I remember telling the students, I said, look, if you understand the calculus, which you guys do, and you understand optimization, and you understand correctly how to set things up and solve multiple variable calculus problems, I say you've come a long way, but that's not the only problem. If you also know how to solve the systems of linear inequalities, because those are maybe even more real life than the other ones, okay? And I would tell the students that if you have these skills and you know some simple programming, you actually can go very far. I have a young friend who works for Apple up in Cupertino. That's the one that looks like a big spaceship. And he was, I've told the story a few times. He was the one, sophomore year gets the paid internship at Qualcomm, and then the next year with a startup that immediately hired him when he graduated. Worked for a few years, went back to UCSD, got his master's degree. He told me the two most important classes he's taken in his entire life, by the way. He's a software engineer for Apple. The two most important classes were linear algebra and discrete math. He says there isn't any programming class where he's used any of it ever. He says you learn all the languages when you get the job, but you learn how to learn languages from your programming classes and your data structures and stuff. But he said it all comes down to linear and discrete because everything's about writing algorithms, which is 100% math. So I just saw him last week. I went to a wedding up in that area, and he was telling me, he goes, yeah, we just hired this person from UCSD with a math degree and some basic computer skills. Just graduated, had 1 year of work experience. 130 grand. I said, with a bachelor's degree and no experience? Well, I had a year of experience. It was really good experience for a year. They just hired, they said, what they're looking for, they're not looking for anybody with computer science degrees. Those are a dime a dozen. They're always looking for math people who can program. People have been telling you something completely different. I always tell people, engineers and computer scientists, great degrees to have. And there is no field that is more flooded than those two. You can get a great job, but you become the most replaceable cog in the wheel because there's 1,000 people that will happily take your job and maybe for less money. So that's why you got to go on and get the higher degree at some point. So he was telling me this. So going back to the 90s, I had a student, and he aced all my calculus and linear, and he was terrific in this programming class. And about a year later, he dropped out of school, he told me. He interviewed and got a job at some place. I don't even remember the place, it's not important. He sent me a copy of his first full-time paycheck. He didn't have a degree. What he had was really good skills, lower division skills, mind you. He sent me a copy of his first paycheck. This is in the 90s. It was several times more than I made. And it just had a little note on the bottom that said, "You were right, thanks." He got hired. Technically, he would have been a junior in college. He was hired for several $100,000 per year. This is in the mid-90s. Because at his interview, he showed them how to problem solve multiple types of problems, and he could write a program. He was smarter than anybody that worked for the high-tech company because he knew how to use his math and computer skills. He didn't just take classes and get A's. He actually understood how to use them. He never went back to school. He didn't really need to. I kind of wish he had, because then I would have brought him back and told you guys the value of education. But I was kind of blown away. And, no, if that's you, I think I should get a finder's fee or something, 5% at least. But he said he negotiated, he convinced them, I guess he gave a great interview. But the point being, programming skills, the calculus skills, and the linear algebra skills, there was no problem that he could come across at that point that he couldn't solve using that. He didn't need higher levels. Now, having more math and higher level stuff, he could have handled bigger problems, but this company didn't have bigger problems than that. The problems they needed him to solve, he already knew how to solve. It was pretty darn impressive. But I don't need you to program, but what I'm telling you is when you go out and you work, if you're not a computer science major, you're just like, why would I have to take programming? No, you should take some programming. Is there any math majors here? So you probably have to take at least one programming course, I'm sure, for your degree. Usually as like a general ed kind of thing. But if you don't, it's a good idea to have it because the next job, they want to see skills. They want the degree, but they want to see skills that aren't just in that area. So it's really good if you're a math person. Now, I have a son who wants to study computer science, but I'm trying to get him to lean more towards math because he's really good at math. I said, take some computer science, but lean towards the math. And there's a lot of reasons. San Diego State. Anybody going to state or planning on going to state? Great place to go for computer science. Good luck. The sheer numbers say it's really hard to get in. So I've had many students over the years, I said, don't go in as a computer scientist, go in as a math major. Minor in computer science. And I go, why would I do that? I said, first of all, when you apply to grad school, they'll take you over to computer science 100% of the time. The math degree will trump the computer science degree for grad school in computer science 100% of the time, as long as you have some programming skills. but also when you go to the higher levels, everything's based on the math. And so I've had several students over the years, they applied to state, couldn't get in computer science, but they got in math, and they just took all the computer science courses anyway, but from a different department. And they told me, they said grad school was a piece of cake. Everybody wanted them, as long as, of course, you perform well. They don't always tell you this, but there's always a back door. You want to be an engineer at state, you can't get in. Maybe declare a physics major or something like that. Because are you going to take a lot of the same courses? Yeah. And by the way, after a year, you can always switch because you have a really good record and you're already in. There's a lot of things you can do if you can't get in directly. But having the strong record is really helpful. Getting A's is, encouraged. I don't think anybody will tell you don't get A's. All right, can you stop that?